In this video, I'll be doing energy analysis in SHM. So, energy in SHM. Suppose that if any particle is there, I have taken this example that it starts SHM, executing SHM. So, suppose that the maximum displacement is possible up to amplitude, and it is performing SHM. That means we know that f is equal to minus kx and m into a is equal to minus kx, so acceleration will be minus k by m into x, and we know that a is equal to minus omega square x, so this will be omega is equal to under root of k by m. We have seen already these things, and already we knew that time period is equal to under root of m by k. But our question is, what about the energy at any instant of the particle? Let's say particle is at point P, x displaced from the mean position, then what is the value of total energy and kinetic energy and potential energy? Correct? So, if you see at point P, we know that if velocity is v at this point, this velocity v will be v max, and here velocity v will be 0. We know velocity in SHM is equal to omega under root a square minus x square at any general point, right? So at P, let us, if velocity is Vp, then Vp can be written as omega under root a square minus x square. Perfect. And if the particle has mass m, then kinetic energy in SHM can be given as half m into Vp square generally, and this is the general format. If I substitute the value of Vp, this will be omega under root of a square minus x square whole square. This will become half m omega square a square minus x square. Perfect. Now from this relation we know that k can be written as m omega square. So if you substitute this m omega square instead of this, we can find k e kinetic energy will be half k into a square minus x square. Perfect. Now we need to talk about potential energy, right? And once I can calculate the potential energy, now we can add up both these and we can find out the total energy. So for potential energy, we need to see that this particle is, let us say, they said at this point, which is x away. That means restoring force F is acting, which is minus kx, right? Suppose that if this particle displaces certainly dx distance, and the force is for small displacements we can assume which is approximately constant, that means small work done dw will be is equal to f dx. Correct? Okay. And this f will be is equal to minus kx into dx. So this is f dot dx. So obviously both are having 0 degree angle, so this is cos 0. So now dw is equal to minus kx dx. Now we know that this small work will be converted into potential energy, right? So we can calculate w from point P to O will be the integral of minus kx dx, and at O I was at x equal to x, and at O x will be 0. So this will be minus kx square by 2, limits are from x to 0, so this will give you kx square by 2, 0 plus kx square by 2 while putting the limits. So this will be work done from p to 0. This work done will be delta u for p to 0. So now I can write it as, this can be written as u at p minus u at 0 is equal to kx square by 2. Now this u at o, that means u at o means u when x equal to 0, we need to assume this is 0. This is our pure assumption. It may not be 0 also. If in that scenario, if it is 0, then up can be written as kx square by 2. Okay, so we obtained the value of potential energy and kinetic energy at p is half k a square minus x square. Then we can find the total mechanical energy. Total mechanical energy will be is equal to up plus kep. So at point p, potential energy plus kinetic energy at p. So E will be kx square by 2 plus half k into a square minus x square. Then it will be is equal to k by 2 can be taken as common. This is x square plus a square minus x square. This is cancelled out, so this will be half k square. So this is the total mechanical energy in SHM, which will be constant. E will be constant throughout the journey of the particle. If no energy loss. If no energy loss anywhere, then we can say this is going to be the total energy in SHM at any point. Now we can also draw a graph for the better understanding. So the graph, so kinetic energy we obtained half k into a square minus x square. Potential energy we obtained half k x square, and total energy we obtained half k a square. So if I draw the graph of kinetic energy and potential energy with respect to x, this is x, then obviously total energy will be constant. Suppose that I am taking, this is x equal to positive a and this is x equal to minus a. We had that particle at x equal to 0. So we know that at x equal to 0, this will be 0. Potential energy will be 0 at 0. We already assumed this also, and we can also put x equal to 0 and we can find. So if x equal to 0, this potential energy function will be like this, right? So this will be a parabolic function while having the vertices at origin. So in mathematics you can see this thing. Okay, and of course kinetic energy will be the reverse graph. So reverse graph will be like this. Getting my point? So here there are 2 points which you obtained where you are seeing that kinetic energy and potential energy are equal. So this is for potential energy and this was for kinetic energy, right? So this is for U and this is for kinetic energy. So we can also understand about these 2 points where energies are equal. We can find first of all these points. So when kinetic energy and potential energy are equal, so if you use that equality, half k into a square minus x square is equal to half kx square. Is that clear? Both the functions are having same value at this point, let's say p and p dash. Then we can solve this. We get a square minus x square is equal to x square. So 2x square is simply a square. X will be is equal to a square by 2 and under root, then x will be plus minus a by root 2. So I would suggest you to remember this result. This can be directly asked in the question paper. Okay, so this point is x equal to minus a by root 2 and this is x equal to plus a by root 2. So at these 2 points, kinetic energy and potential energy will be equal, though mechanical kinetic energy is having the fixed value in this region, which is this value. So this line is representing the energy half ka square at any instant. So this is graph for potential energy and kinetic energy, and of course this line is representing E, total energy. Correct? So this is about energies and SHM. I believe that you understood it. This is really important. Okay.